There are multiple problems on our problem set that refer to xenon difluoride, so we're going to knock them all out in this one video. Let's start with drawing the Lewis structure. Xenon is a noble gas, comes in with 8 valence electrons. Fluorine is a halogen. It's in group 17, so 7 valence electrons for fluorine, and there's 2 of them. 14 plus 8 is 22 valence electrons. Fluorine is the most electronegative element, so we'll put xenon in the middle or the center, surrounded with the 2 fluorines, and put a bonding pair between the terminal and the central atom. And we are going to, each of those bonding pairs is going to use up 2 electrons. We have 18 left. Let's get the terminal atoms in octet by giving each of them 6 more valence electrons because they already have 2 in the bonding pair. That's how you get them the octet. And that's going to use up 12 more of electrons, so we're down to 6. Put those 6 around the central atom, xenon, which does have access to d orbitals. So all your period 3 and below on the periodic table elements will have access to d orbitals, and they can have an expanded octet. Now, because we only have single bonds here and we started with 22 valence electrons, there is no way to satisfy the octet rule. So this cannot be possible with xenon and 2 fluorines. So we just drew the Lewis structure. You can check out the formal charges. There's really no other way to draw this, but the formal charge on all of these is going to be 0. And if you want to do that real quick, you can get the formal charge by getting the number of valence electrons in its neutral atom, subtract the number of dots, that represents the unbonded electrons, and then subtract the dashes or lines, or the number of covalent bonds, which represent each atom's shared electron. So if you do that, all the formal charges are 0 for all of them. But again, this is really the only way you can draw that. Now let's do step B, or the second bullet. Describe the VSEPR geometry. And we have, look around the central xenon, you have 1, 2, 3, 4, 5 regions of electron density, or a steric number of 5. So when that's the case, the electron domain geometry is trigonal bipyramidal. There it is. Now, not all of them are connected to atoms, only 2 of them are. In other words, you have 3 lone pairs, so that structure is going to be linear. So let's draw that again, a little more 3-dimensionally. So we've got fluorine on the top and bottom, and then this one is just on the plane, perpendicular, and that's going to be a lone pair there. And then you can draw a lone pair coming out of the screen 120 from that lone pair, 120 degrees, and then one going back there. That's another lone pair there. So these are all 120 degrees from each other, and then the fluorine are 180 degrees from each other, making this molecule linear. So there's your answer for the VSEPR question. Now the last part is this polar or non-polar? Now this bond here is polar, that bond there between the fluorine and the xenon, because fluorine is much more electronegative. Xenon is a noble gas, so it's a very low electronegativity. And so there is for each of these bonds is polar, but because of the symmetry of the molecule, those dipoles, they cancel each other out. So there are no net dipoles on this molecule. It is non-polar. The molecule is. So molecules can have polar bonds, but if they cancel each other out, then the molecule can be non-polar, as in this case.